And every year or twice a year, I forget about the time change, and then tell myself I won't forget next time, and forget. So, but it seems we figured everyone's here. So
yeah, we were optimistic. My strategy is usually just change all my clocks as fast as possible. As soon as I notice that my phone and my oven don't match, I fix the oven.
Yeah. Okay. Well, anyway, we converged on this time. So yeah, I guess this is the right time, and here we are. Okay, should we get going?
Yeah.
All right. Okay, so last time we discussed like the definition of zero knowledge. And there was a lot of discussion on just like what it means, the how it's formalized via the notion of a simulator, and how the notion of a simulator, which seems somewhat technical, really is capturing that the verifier learns nothing from the prover other than the fact that the statement the prover is claiming is in fact true. And there was just discussion about how zero knowledge like almost feels like it contradicts soundness, like security, but it doesn't. The simulator is not actually acting as a convincing prover. Rather, it is capturing that anything that the verifier learned from talking to the prover, it could have efficiently computed on its own. That's very different than the simulator itself being able to kind of act as a convincing prover that's answering verifier challenges, that it are unpredictable. And so last time I used as an example, without going into details of how it works, Schnorr's Sigma protocol for knowledge of a discrete logarithm. So today we're going to see the details of that. So I'm going to tell you what is a Sigma protocol. So Sigma is like the capital Greek letter Sigma. So I'm going to tell you what, I'm going to define what a Sigma protocol is, and then we're going to cover Schnorr's Sigma protocol for knowledge of a discrete logarithm. And if there's time, we'll talk about Peterson commitments. So this is a very important commitment scheme. It satisfies a property called additive homomorphism. And it's also binding and hiding. And so we'll see how long it takes me to cover Sigma protocols and Schnorr's Sigma protocol, and make the judgment call about whether it makes sense to discuss Peterson commitments now or next time. And this is a really important topic kind of as a standalone thing, but the main reason to spend an entire session or two on these topics is that polynomial commitment schemes that use elliptic curve, that use cryptographic groups, are all kind of built out of Peterson commitments and techniques like Schnorr Sigma protocol. So from the Snark design perspective, this is more a building block towards what we really care about. From the like cryptography as a whole perspective, it's a very important topic in its own right. So with that, I can just dive into what is a Sigma protocol. But maybe I'll pause real fast, see if anyone wants to begin with a question about ZK or anything I just said about what we're going to discuss today.
No questions and no hands.
Okay, sounds good. All right, so yeah, a Sigma protocol is a 3-message protocol where the prover speaks first. So the prover will send a message. I think today I will denote that message A. The verifier will respond with a random challenge, which I will denote E. And then the prover will respond to the challenge with a message Z. And then the verifier will either accept or reject. And so it's called Sigma protocol just because, like, it's kind of silly. The Sigma, if you draw it a certain way, looks like 3 messages, I guess. That sort of looks like, a Sigma. I don't know. That's apparently why they're called Sigma protocols. Yeah, it has nothing to do with sums or anything really. It's just the message pattern sort of looks like the capital Greek sigma or something to that effect. So so in a Sigma protocol, the prover is claiming to know a witness W satisfying some property. And so in Schnorr's Sigma protocol, which I think is the most important example of the Sigma protocol around, it's a discrete log that the prover is claiming to know. So for Schnorr's, there will be, both the prover and verifier will know, 2 public group elements, G and H, from some cryptographic group. In practice, these are elements of an elliptic curve group, and the chapter in the book, chapter 12, where I discuss Schnorr's Sigma protocol, covers some basic background on elliptic curves, but like really, I'm not going to cover that today because it just doesn't really matter. Like all you need to know is that a group is a collection of elements with an operation, which today I'll denote by multiplication. And so you can take any 2 group elements and multiply them together. And every group element has an inverse as well. And an inverse of a group element G is just if you multiply them together, you get out the identity group element, which we denote 1. Every multiplicative group has some identity element. This 1 means 1 times any group element is just the group element. Yeah. Okay. So that's really all you need to know about elliptic curve groups today. There might be one more fact that I bring up later about these groups being what are called cyclic groups, where they have some generator. Don't worry about that right now. So anyway, so in Schnorr's Sigma protocol, the prover and verifier sort of have agreed on these group elements G and H, and the prover is claiming to know a W such that G to the W equals H. Okay. And yeah, so that's what's going on in a Sigma protocol. And so of course, if the prover wants to prove it knows W, it could just send W to the verifier, but that wouldn't be zero knowledge. So a Sigma protocol is sort of meant to achieve the same effect as sending W to the verifier, but while being zero knowledge. So leaking no information whatsoever about W other than that the prover knows W. Okay, so what are the formal requirements of any Sigma protocol? So let's say the first is just completeness, which says, if the prover indeed knows W and follows the prescribed protocol. Let me summarize that by just saying if the prover is honest, the verifier will accept, say with probability 1. So just will always accept, AEZ. Okay, the other 2 properties are more interesting. So the security or soundness notion that's relevant to Sigma protocols is called special soundness. Okay. And so this says, given, well, let me put it this way. There is an efficient procedure, an efficient algorithm. By efficient, formally we mean polynomial time, but just think it's fast. It's an efficient, it's a fast algorithm that, given as input any 2 accepting transcripts for the Sigma protocol, accepting transcripts, meaning, they cause the verifier to output accept. Let me say AEZ and AE prime Z prime, so that share the same first message A, but have different verifier challenges. The algorithm outputs a valid witness W. Okay, so given, again, to summarize, it's just given any two transcripts that share the same first message, one can derive the witness. Okay, that's special soundness. So intuitively, special soundness is like stronger than standard soundness. Standard soundness just meaning that if the verifier accepts, then the prover's claim is true. For the following reason. So I think of special soundness as the following. If after sending the first message A, the prover is prepared to answer two different challenges, E and E prime, the prover must know W. Okay, so what's going on is, like in the protocol itself, the prover only gets one challenge, E. Okay, but if there's only one E it's prepared to, successfully respond to, it's very unlikely to get that single challenge E. It has to get really lucky if the verifier happens to pick that one challenge it's prepared to answer. Special soundness says if it's prepared to answer two challenges, E and E prime, it must know W, just because given its answers to E and E prime, you could actually quickly figure out W. So that's sort of my intuitive personal definition of special soundness. Right. So that means from the verifier's perspective, if it sends the challenge E and gets a successful response from the prover, all the verifier knows for sure is that the prover was prepared to answer that one challenge, right? But unless the prover got really lucky, it was, almost certainly prepared to answer some other challenges as well. And so the fact that it was prepared to answer, many different challenges means, but special soundness implies that the prover, in that situation actually knows W. Okay. Any questions about the special soundness definition? All right. And then the third property is honest verify.
One question is coming.
Question, please.
Yep.
I had a quick question, Professor. That is there a bound on the number of queries that you get to make?
To the prover?
Yes.
Yeah.
So prover is answering this queries, right? So there must be a bound.
Yeah. So in one run of the protocol, the verifier only gets one. Okay. And now, in practice, we wind up typically running Schnorr Sigma protocol non-interactively by applying fiat Schnorr. And that sort of automatically enforces that this only one challenge property, because with fiat Schnorr, if the first message is A, fiat Schnorr sort of deterministically sets the challenge to be the cryptographic hash of A. And so that means the use of fiat Schnorr sort of bakes in as well that there sort of is only, at least for any particular first message, there's only ever one challenge that the prover kind of gets queried at. But anyway, so you should think of it as you're just going to run this protocol once, whether it's interactive or whatever. And so there's only going to be one challenge ever sent to the prover. But if the prover is able to answer that challenge, it was probably prepared to answer all sorts of challenges. Because if it was only really prepared to answer one challenge, then it's very unlikely to be asked the one challenge in this. Does that make sense? I don't know if you're muted now or I'm not hearing the response.
I was trying to give her a chance to speak again, but she did not. So.
Okay. Okay. All right. So feel free to interrupt if there's technical issues or anything. But yeah, hopefully that answers the question. Other questions?
Nope.
Okay. I am getting some background like white noise now. I don't
Me
know.
too, and I don't understand why, because it's not coming from you and it's not coming from me.
Okay. All right. Well, I'll just prepare. I'll just proceed for now. But maybe I don't know. Maybe you'll find a way to make the white noise go away. Okay. So then this is the standard like completeness and like a special kind of soundness requirement. And then the last property we care about is zero knowledge. Like, does the proof actually leak any information about W? And so we require like no. Specifically, we require honest verifier, perfect zero knowledge. Okay, so this means that kind of just repeating the definition from last time, there is a randomized algorithm called the simulator that outputs transcripts AEZ, and the simulator is randomized. And so the output of the simulator should be distributed. So because it's randomized, it's really outputting. You think of it as producing a distribution over transcripts, right? Because you like run it once and you get out like a random transcript. So there's implicitly just the probability distribution over transcript of the output. So the distribution over transcripts should be the same. Perfect means like the exact same distribution as the transcripts produced when the honest prover talks to the honest verifier. Yeah, so that's honest verifier, perfect zero knowledge. And I discussed this a little bit last time. It's like if you really run the protocol interactively, there's nothing forcing the verifier to be honest. It could kind of not send a random challenge, send some a challenge that's not distributed uniformly at random over the challenge space. But in practice, we'll typically run something like Schnorr Sigma protocol with fiat Shamir, and then the verifier is kind of cut out of the protocol completely. The challenge is determined just by hashing this message, and that sort of eliminates any distinction between honest and dishonest verifiers. So that's what's required out of Sigma. Okay, questions about what is a Sigma protocol?
I didn't understand this sentence at the end. So they're saying like it's identically distributed, which is fine. That's kind of part of what you're defining as ZK in the simulator. But then you say honest prover talking to honest verifier ZK, and I'm kind of confused by the ZK.
Oh, sorry, that might have just been that.
Honest. Okay, cool.
Yeah, sorry. I just was doing too much at once and must have said ZK and then wrote it without meaning to. Sorry.
All good.
Yeah, great. Okay, so that's what we require, and I guess I'll remind you, like, special soundness sort of means we discussed it. That it almost feels like ZK and soundness or special soundness are in contradiction with each other, that you can't have both at once. Because doesn't special soundness mean that like if I give you a prover algorithm, I can figure out the witness? And the answer is, and if of course, if the verifier could figure out the witness, that would be like a complete violation of ZK. So how can you have special sounds in ZK? Hi. And the answer is there's no contradiction because the verifier in this protocol only gets to ask like one challenge of the prover. And therefore, there's like kind of no way for the verifier itself to get these two transcripts with the same first challenge, first message, but different verifier challenge. Yeah, so there's not actually a contradiction. Again, like the verifier itself is not given the ability to identify two transcripts of this form. It's only given the ability to kind of get one transcript from out of the prover rather than two. And if it does kind of run the prover from start to finish multiple times, it's basically never going to see the same first message. And yeah, so that's why there's no contradiction. The verifier in this protocol only is never going to wind up with two transcripts of this form, and therefore never going to be able to identify the witness. In fact, won't learn anything at all about the witness that's formalized by the HTTP requirement. So with that, let's just dive into Schnorr's Sigma protocol. So again, they both know G and H, and the prover wants to convince the verifier knows the W such that G to the W equals H. Now, I normally like to present Schnorr's Sigma protocol with a sequence of attempts at designing, a protocol that works, and none of the attempts work until like the fifth attempt when we finally fix all the issues, right? So so attempt one, which I kind of already mentioned, would just be to have the prover, of course, send the witness to the verifier, and the witness would check that in G to the W equals H. Okay, that's great. That's complete and special sounds, but it's not zero knowledge at all. Okay, so that's attempt one. That doesn't work. So attempt one was he sends W to the verifier, and so this is in ZK. Okay, so attempt two. So now, in attempt two, the prover might try to send two different things to the verifier. It might send so the prover might pick a random R, a random exponent R. Okay, and it might send not the witness itself, but rather the witness plus R to the verifier. All this, by the way, all this arithmetic is, this is going a little bit more into these elliptic curve groups, but so the space of possible exponents is actually like a finite field, and so this is not integer arithmetic. Addition modulo what's the size of what's called the scalar field of the group. So think of the scalar field as just like the field of possible exponents. Yeah, so like if W plus R gets too big, you sort of wrap around back to zero. So you can take two non-zero exponents and add them together and get out the exponent zero. The same way you can take any two field elements and add them together and get zero, even if they're both non-zero. So I'm just trying to skip the background on the elliptic curve groups for understanding Schnorr's protocol. Yeah. So anyway, so the attempt here would be, rather than sending W explicitly to the verifier, because that would violate zero knowledge, the prover could send W plus R, as well as R. Okay. And in this way, like the attempt here, of course, doesn't work, but the attempt here is like R is being used to mask W. And so this way, the prover is never explicitly just telling the verifier W, because it's sending W plus R, and R is random. So no matter what W is, W plus R is a random exponent. Okay, they can't only send W plus R, but that would just be sending the verifier some random garbage. So it has to send something else. And it could, if it sent R, right, then then you're back in the situation of attempt 1, but again, it doesn't work, right? So like if the prover sent W plus R and R, the verifier on its own could compute W as W plus R minus R, and check that as before in attempt 1, G to the W equals H. Okay, and so again, you get, so the prover, and just summarize, the prover sends W plus R and R for random R. Okay, and this is a step in the right, like towards how Schnorr Sigma protocol actually works, but it's not all the way there. So what's going on? Like, if the prover just sent W plus R, this would be zero knowledge, right? Because W plus R is just a random exponent completely independent of W. W has been masked by R. Okay. The problem is, like, that's useless as far as the verifier is concerned. That's just like some random garbage. So the prover is also sending R, and together, that's as bad as sending W as far as zero knowledge goes. Okay. So that's also not okay. Okay, but it had this idea in it. Like, the idea here was to mask W by adding some random junk to it. Okay, and the problem here is the prover is also telling the verifier, the junk, and together, this lets the verifier like remove the junk. Which means there was no point to adding the junk in the first place. Okay. So attempt 3 is, let's see. So I sort of just munged attempts 2 and 3 from the book together. So sorry about that. So attempt 4 is the following. Rather than send R explicitly to the verifier, the prover can hide R in the exponent of G. Okay. Okay, and now we're getting pretty close to how Schnorr Sigma protocol actually works, although we're still not quite there. Okay, so this does have the property that, right? So the intuition here is, since discrete logs are, we believe, hard to compute, the verifier, does not learn R from G to the R. Okay. So we're still somehow like conveying, information about R to the verifier here, but we're not. It's not so bad as just sending R explicitly to the verifier, like we did in attempts 2 and 3 together.
In a way, we're committing to the choice of R. Right?
Yeah. This is exactly what I would call an unmasked Peterson commitment to R. So let's not worry about what that means right now. It's just you're exactly right. Like, this is sort of it's like binding the prover to R because there's a unique R. There's a unique exponent. That yields this group element. Let me call this, I don't know, G prime. There's a unique R such that G to the R equals G prime. So sending G prime to the verifier is sort of sticking the prover with that particular choice of R. But the verifier itself, given G prime, does not know R. This is one reason I like multiplicative group notation, because I think of this as hiding R in the exponent. The exponent there is fixed, it can't be changed, but the verifier can't figure out what that exponent is. Okay. And now the verifier can check that. So G to the R is actually enough information about R for the verifier to sort of do its check from attempts, the previous attempt. So the verifier can check that. what did I want to? Okay, so actually, I call this A. I call this A in the book. There's a good reason for that. This is actually the prover's first message in Schnorr Sigma protocol. So the verifier can now check that. What is the check? A times H equals G to the Z. Okay, so yeah. So if you write out like what this check is saying, this is checking that G to the R times H equals G to the W plus R. Which if H indeed, as the prover claims, is G to the W, this is the same as saying this is the same as checking that G to the R plus W equals G to the R plus W. So yeah, so this is just intuitively this check here, A times H equals G to the Z. This is doing the verifier's check that what did the verifier check before? Yeah, so W plus R was Z. Yeah. So the verifier's check before was Z equals R plus W. And so what I wrote here, this A times H equals G to the Z is sort of doing this check in the exponent. Okay, and this is exactly the way to think about things with Sigma protocols for discrete logarithms, like what's going on in the Sigma protocol. It's like you pay attention to the exponents, and you wind up checking, that two exponents are equal. But because discrete logs are hard to compute, the verifier doesn't actually know what the exponents are. So that's how all the magic works out. The verifier doesn't learn anything because it doesn't learn what the exponents are, but it's nonetheless able to confirm that the exponents are equal, and therefore the prover is being honest over there. And yeah, so this A times H equals G to the Z thing, again, A is like G to the R, and H is supposed to be G to the W. So this is just like checking that G to the R plus W equals G to the Z, which is like checking that R plus W equals Z. So A times H equals G to the Z is checking that R times R plus W equals Z in the exponent.
And is it fair to say that the prover is sort of sending one piece of data in the exponent and one piece of data that's not, and so
Exactly.
has
Exactly.
to do the
So in this attempt, the prover is sending, another way to describe the attempt is that P sends R hidden in the exponent G, but sends Z, which if is supposed to be W. So I put a question mark here, like a plain R plus W in the clear. Okay, and then the verifier does the check in the exponent. It has to do the check in the exponent because once something is hidden in the exponent, the verifier has no way to get out of the exponent, so it's got to move Z into the exponent. Yeah, which it can do. Like if you send a verifier something in the clear, it can move it into the exponent. What it can't do is take an exponent and get it out. Kind of a one-way function. Yeah, you can take things in the clear and move them into the exponent, but you can't take exponents and and move them into the clear.
That is a discrete log assumption.
Yes. Right? Yes, exactly. The discrete log assumption is that if I give you like G to the R for random R, it's computationally intractable to figure out what R is. So that's saying, you can't take things out of the exponents unless you already know them. Okay. So yeah, this attempt is pretty close to Schnorr Sigma protocol. There's a very good indication that it doesn't actually work, and that indication is there's only one message here. There was no verifier challenge. Okay, and so we know Schnorr Sigma protocol is a Sigma protocol. There's got to be a verifier challenge. So this can't work. So why does this not work? So this fails. And the reason it fails is it's not secure. It's not special sound. Okay, it is HVPZK. Okay, but if something is HVPZK plus non-interactive, so just one message, as this is, that does violate sound. Right. So all this discussion we had like last week and earlier today, that HVPZK and special soundness are not in contradiction to each other. In fact, they are contradictions if there's no interaction, right? Because the simulator outputs accepting transcripts. That's what HVPZK means. In this case, the accepting transcript is just, there's no challenge. It's just, A comma Z, where A is, if the proof is honest, is G to the R, and Z is R plus W. But accepting, if it's a non-interactive protocol, this is a convincing proof, quote proof, because it's not a secure protocol, right? And so that means that there's no security. Without knowing W, the prover can indeed produce these accepting transcripts. And I guess what's going on is the attack is whatever the simulator does here. So let me just remind myself what the simulator does. So the simulator, this would also be, AKA in this case, a cheating prover. What it can do is it can choose Z first, say at random. So this is a random exponent. Z is now just a random exponent. And then it can backfill A. So it can set A to be, what would it be? A would be G to the Z times H inverse. Yeah. And then, under this definition, remember the verifier's check here is A times H equals G to the Z. If A is G to the Z times H inverse, then this becomes just G to the Z. Right. G to the Z times H inverse times H is just G to the Z. And so the verifier check will pass. And, anyone can do this. Anyone can choose Z at random and then set A to be G to the Z times H inverse. So we've sort of seen every permutation here of Schnorr's Sigma protocol that doesn't work. Every attempt here was non-interactive, so it couldn't work. Right? The first two attempts violated zero knowledge. First two attempts, like attempt one was just send W. Attempt two was send W plus R and R. Those violated zero knowledge. Attempt attempt four. Attempt four is zero knowledge, but it's not secure. It's not sound, and it can't be sound because it's non-interactive. And zero knowledge plus non-interactive together imply insecure because the simulator itself is an example of a cheating tool. Okay, so that's everything that doesn't work. So now we'll finally get to Schnorr Sigma protocol. Okay, before we actually see it, does anyone want to ask anything about these, attempts that didn't work?
Why did the last one not work again?
Okay, the last one was the verifier sends G to the R and R plus, the prover sends G to the R and R plus W. Right, and the verifier checks that, call that G to the RA. The verifier checks that A times H equals G to the Z. Okay, and it didn't work because it's insecure. It's not sound. Okay, and the way to see it's not sound is here's the attack. And so if the prover is like honest, like first it selects A, and then it chooses. Well, sorry, like it's sort of like it picks R first, that determines A, and then Z is implied by the witness. So it's like A first, and then that implies Z. The attacker chooses Z first at random, and then backfills A. Okay.
But was there something like why they're not able to do that because of the interaction?
So in Schnorr's actual Sigma protocol, which I'm only now about to tell you how it works, they won't be. This attack will break down because of the interaction.
Got it.
Yeah. So just to say this one more time, this final attempt that didn't work, it was zero knowledge. It was not sound, and in fact, zero knowledge and soundness are in contradiction for a protocol like this attempt because it's non-interactive. And zero knowledge plus non-interaction means no security, right? Because the simulator itself actually, the simulator itself, whose existence is guaranteed by the zero knowledge property, is acting as a cheating prover if there's no interaction. Yeah. Now again, fiat Shamir is a way around that, but there is no fiat Shamir. So like, yeah. So no interaction with no cryptography makes HVPZK and soundness contradict each other. You can't have HVPZK and lack of interaction together if you want sound. Schnorr's Sigma protocol addresses the issue by bringing the interaction, and then you can have both HVPZK and soundness. Okay, so here's Schnorr's Sigma protocol. All right, so here the prover does send A, which if it's honest, this will be G to the R, where R is random. R is the random exponent. Okay. Then the verifier sends a challenge Z, a challenge E, where you should think of E also as like a random exponent. Okay, and then what the prover replies with is Z, which is claimed to equal W times E plus R. Okay, and the verifier does the same check as before, that the verifier checks that A times H to the E equals G to the Z. Okay, and so this is, so the previous protocol, the previous attempt that was non-interactive was Schnorr's protocol, but with E fixed to 1. Right. And, so the previous attempt, I just said, there was no E. The prover just sent one message, which had A and Z in it. And the verifier's check was A times H equals G to the Z. So that's it. That's exactly what you did here by fixing E to 1. A times H to the E is just A times H if E is 1. Okay. And so, yeah, like again, the key problem with the previous attempt, the reason it wasn't secure was that there was no interaction. Effectively, it was literally Schnorr's Sigma protocol, but saying, "Oh, I don't like the interaction. I'm just going to fix the verifier challenge to 1." And of course, if a prover knows the verifier challenge in advance, you tend to lose all soundness. And so, once you see Schnorr's Sigma protocol like that, you would of course, say the previous attempt must be insecure, that it's not sound, since it's just fixing the verifier challenge to 1. And what it's getting rid of the security benefits of the verifier challenge. So that's Schnorr's Sigma protocol, and now we're just going to work through the 3 properties to establish that it's indeed complete, special sound, and honest verifier, perfect zero knowledge. We're gonna establish each of these in turn. Does anyone want to ask a question about what's happening in the protocol?
So with lack of interaction, we really meant knowing randomness beforehand, as in
That's one way to view it. Yeah. I couldn't put it that way because I hadn't told you Schnorr Sigma protocol yet. But basically, the final failed attempt is just Schnorr Sigma protocol with the challenge known in advance and in fact fixed to 1 for simplicity. And of course, that can't be secure. It's just like this with the sum check protocol. If the prover knew in advance what the verifier's first random challenge would be, it can easily cheat. It sort of sends a message that looks fine for that challenge only. But is terrible for all other challenges. But the verifier only winds up checking it at this one challenge that the prover knew in advance. And so same sort of thing here. It's like that final attempt that didn't work. It just take Schnorr, fix the challenge to 1. Of course, you lose security. Okay, so yeah, I think there's I wanted to highlight two perspectives or two things about Schnorr Sigma protocol with these attempts that didn't work. So maybe there's like 3 intuitive ideas maybe captured by each attempt. Okay, so the point of this R is to mask W so that the verifier doesn't learn anything about W when the prover sends Z. Okay. So that's why the R is there. Okay. It's to give 0 knowledge, to make sure that the verifier doesn't learn anything about W. So R is there to mask W. But the prover can't send the mask, this R, in the clear to the verifier, because if the verifier knew R, then it could just wind up removing the masking from the final message Z, and therefore R wouldn't actually be helping do any masking. So the mask is hidden in the exponent so that the verifier doesn't actually learn the mask, and yet the mask is still like enough information about the mask is revealed to the verifier for the verifier to ultimately do its check. But the mask itself is not revealed. And so, yeah, the mask is there to protect 0 knowledge, but it's hidden in the exponents, and therefore the masking is actually effective. It can't be like undone by the verifier. Okay, and then this E is there to make sure that the prover actually knows W. It's for security. It's to make sure that you can't do this attack from before, where you choose the last message sort of first, and then backfill the first message without knowing the witness. And as we'll see, special soundness formalizes that. It's saying if the prover is kind of prepared to answer 2 different challenges B, it must actually know W rather than just backfilling, a first message based on the last one Z or something. Okay, so those are all the moving pieces of the protocol. R is there for 0 knowledge. E is there for soundness. If you explicitly send R to the verifier rather than hiding into the exponent, stuff won't work out. If you get rid of the random challenge, stuff won't work out. If you put it all together, everything works out. You have both 0 knowledge and sound. Other questions? All right. So yeah. So let's just run through these quickly. But this is just like formalizing what it said. So completeness. So the completeness says the verifier will always accept if the prover is honest. So this is just like this verifier check was designed to pass if the prover is honest. But like just remember, if the prover is honest, A is G to the R. So this check turns into G to the R times H to the E equals G to the Z. But H, if the prover is honest, is G to the W. And Z, if the prover is honest, is W times E plus R. And so, yeah, this right hand, like G to the W to the E is W times E. And if you multiply that by G to the R, so this just equals G to the W times E plus R. And so the check passes. The check was like, this check was just designed so that this outgrew. Now, special soundness, this is where things start to get interesting. So let me just gather my thoughts for a second about how I normally like to present this. Right, so here we're given two transcripts, A, E, Z, A, E prime, Z prime. They both are accepting transcripts, meaning that A times H to the E equals G to the Z, and A times H to the E prime equals G to the Z prime. Okay, and so the way to think about this is the check is, you think about the check as doing a check on the exponents, even though, you know, the verifier doesn't know or the extractor doesn't necessarily know the exponents. In particular, you know, A is G to the R for some R, but the extractor doesn't know R. Okay, the extractor is this procedure where we're trying to go from these two accepting transcripts to. Okay, so let's just write out what's happening in the exponents here. Right, A is G to the R for some R, and H is G to the W for some W. So in the exponents, this is checking that R plus W times E equals G to the Z. Does the extractor knows Z? So sorry. Okay. Bear with me. I should have prepped this a little bit, but I'll get it right. Yeah, and so this is not known to this extractor procedure that's trying to take the two transcripts and spit out W. Let me call that like the E for extractor. So R is not known and W is not known. But they exist, right? Like this R is just where A equals G to the R for some R, and this W is you know, H equals G to the W for some W. So the extractor doesn't know R, it doesn't know W. It's going to wind up solving for them. And so this check is equivalent to checking that R plus W times E equals Z. And similarly, this check is equivalent to checking that R plus W times E prime equals Z prime. Okay. Yeah. So what the extractor does know, I'll circle in blue. So the extractor does know E and Z, and E prime and Z prime, because those are in these two transcripts that the extractor is handed us. So red circles are not known to the extractor, blue circles are. Okay, so what we have here is we have two linear equations in two unknowns. Right, the unknowns are R and W. So we can just, with simple linear algebra, solve for R and W. Okay, and then so the extractor does that and just outputs W. Okay, so that's it. That's special soundness. Now, you know, if you don't like, you might not like how I presented this. You know, I said, hey, you know, there is some R such that A equals G to the R. It's not known to the extractor. There is some W such that H equals G to the W is not known to the extractor. But the extractor does know that these two equations hold, and it just solves the equations for R and W. If you don't like that terminology, like I could give you another description of the extractor, right? So what the extractor can do is the following. This is just an alternative description of it. So it can set W to be Z minus Z prime divided by E minus E prime. Is that it? And by division, what I really mean is, you know, multiply by the multiplicative inverse in the scalar field. But don't worry about that. And indeed, if it, and then you do some algebra and you'll find that under this definition of W, indeed G to the W has to equal H. And why is that? It's because G to the Z minus Z prime over E minus E prime is the same as, it's just some gross algebra. I don't like to do it this way, but you know what? I'm even going to skip this. So you can do some algebra. So you like invoke that a times h to the e equals g to the z, and a times h to the e prime equals g to the z prime. That lets you do some algebra and confirm that this quantity is the same as g is the same as h. So yeah, I'm gonna. It'll just take me like 3 minutes to figure out the algebra on the fly, and it won't be that insightful. So yeah, I'll just bail on that. This is So to summarize, the way I conceptualize special soundness is each transcript is giving is because it's an accepting transcript, it tells you that a certain linear equation holds. And there's two unknowns in the linear equation, R and E. But if I give you two transcripts, that's giving me two different equations, so I can solve for both of the unknowns. So the unknowns are R and W, not and yeah, and this is what the solution turns out to be. It's just Z minus Z prime over E minus Z prime. So that's the extraction. Questions about that? Yeah. So the way to conceptualize it is, the check that the verifier does in Schnorr's sigma protocol is testing one linear relationship in the exponents, right? It's testing that, R plus W times E equals Z. It's testing this in the exponent, right? Like really, this A times H to the E equals G to the Z is like some nasty, gross thing that it's hard to think about unless you think about it about what's happening in the exponent. Like it's a very simple test on exponent. So if A is G to the R and H is G to the W, then this check that the verifier is doing is just checking that R plus W times E equals Z. And that's just a linear relationship, right? It's linear in R and W. And so if I give you two transcripts that both accept, I'm giving you two linear relationships that hold, and that lets me solve for R and W. That's all that special soundness is doing. Okay. Questions? All right. And then HBPZK, I'll give you the simulator.
You have some questions?
Oh, there's a question.
Yep. So extractor is an algorithm that can extract the witness over some time or iterations to prove that the prover actually knows the witness.
Yeah. So formally, the extractor here is something that, given two accepting transcripts that share the same first message, can extract the witness. Okay. Now there's a separate. We talked about this last time, and it's worth repeating, which is in snarks we care about knowledge soundness, which roughly says any successful prover must know the witness. And by must know W, that's formalized via this extraction procedure. So maybe my using the word extractor for the special soundness procedure is just confusing things. But must in the sense that there's an extraction algorithm E that if I sort of give it the ability to, like, if I hand it a prover, like an implementation of the prover, that it can like run that run the prover over and over again. The extractor outputs W. Okay, and so special soundness implies knowledge soundness. The reverse is not true. Like there are other ways to establish knowledge. You know, some things that are not special sound might also be knowledge sound. Now, how? Like, you know, how do you show that special soundness implies knowledge sound? Here's the answer. So I'm gonna give you this extractor E that knowledge soundness requires. What E will do is it will run the prover once to get a transcript AEZ. Okay, then it will rewind it to just after the prover sent the first message, and it will restart the protocol with a fresh random challenge E prime, and hopefully the prover succeeds again, answers the E prime challenge as well, therefore giving a second accepting transcript AE prime Z. And then special soundness tells you so that given these two transcripts AEZ and AE prime Z prime, one can efficiently compute the witness. Okay, so yeah, so special soundness, directly it just says, hey, if you somehow give me these two accepting transcripts with the same first message, you can efficiently find the witness. Okay. There's an intuitively that special soundness just feels like it implies knowledge soundness. The hand wavy intuitive explanation is if special soundness basically says if the prover is prepared to answer, after the prover sends first message A, if it's prepared to answer two different challenges, it must know the witness, right? And then any convincing prover must be prepared to answer, many challenges, or else it has to get really, really lucky to get one of the few challenges it's actually prepared to answer. And so that's like the intuitive reason special soundness implies knowledge soundness, right? But the formal reason is if I actually give a knowledge soundness extractor, like an implementation of the prover, it can get the two transcripts, posited by the definition of knowledge of special soundness. How does it get the two transcripts? It does this rewinding thing. It runs the prover once to get one transcript, rewinds it, and starts it again with a fresh random challenge to get the other. So I'm giving you like two different explanations for why special soundness, implies that the prover knows the witness. One is a hand wavy intuitive thing. Special soundness kind of says that the prover is prepared to answer several, two different challenges and must know the witness. That's a hand wavy statement. The formal, the way to make that intuition formal is to say, hey, if I give you a convincing prover, by doing this rewinding thing, I actually can identify two different accepting transcripts with the same first message. And then that's what special soundness formally tells you is sufficient to identify the witness. Yeah, so hope that was helpful. Say again?
Yeah, I had a quick question, Professor. So, do I understand it correctly that given that you give a construction for an extractor, so are you trying to imply that the special soundness is equivalent to proof of knowledge?
I'm saying special soundness. The fact that Schnorr Sigma protocol is special sound implies that it's also a proof of knowledge. It implies that it's also knowledge sound. Okay. And the reverse is like not true. Like something could be knowledge sound without being special sound. In fact, in practice, we would run Schnorr Sigma protocol under Fiat Shamir, okay, to make it non-interactive. And then I'm not even for non-interactive things. I'm not even sure special soundness like really makes sense as a notion. And yet, Schnorr Sigma protocol is knowledge sound even after Fiat Shamiring it. So Fiat Shamired Schnorr's is also knowledge sound. Okay. And the book actually runs through in detail how you show that. Although I've had some complaints that the analysis is not very easy to follow, but it's I can sketch it right now. So, Fiat Shamir. Sorry, let me make sure the background noise went away. So now I'm worried I dropped off the call or something. Can someone confirm I'm still on the call since the background noise went away?
Yep, you're here.
Okay, great. Okay, so remember, Fiat Shamir asked for the prover to output a single accepting transcript of Schnorr Sigma protocol, but now where the challenge is a hash of the first message, right? Such that, again, A times H to the E equals G to the Z. This is Fiat Shamir Schnorrs. This is what the protocol. This is what the protocol is. Okay. And this hash is modeled theoretically as what's called a random oracle. So let me replace hash of A with just R of A for random oracle of A. Okay. And so the way you show that Fiat Shamir Schnorrs is also knowledge sound in the random oracle model is the following. So you run, say you have a prover that's capable of outputting, these proofs. So you run the prover once to get A, comma, R of A, comma, Z. Okay. And then you, I don't want to say this. You sort of run it a second time. I'm being very hand wavy here to avoid, the nasty details that I put in the book, but didn't really do a great job explaining. You run P a second time, but with R, the random oracle, re-randomized. So you hand it a different random oracle in a certain way. In a certain way, yeah. So it's not a complete fresh re-randomization. It's only slightly re-randomized. Don't worry about the details. And the hope is that now the prover in the second run spits out A, comma. So let's say re-randomized to R prime. So this is just a different random oracle. And so now you hope that the prover winds up spitting out A, comma, R prime of A, comma, Z prime. Again, passing the verifier's check. So what is it? A times H to the R prime of A equals G to the Z prime. And if this happens, you're good. By special soundness of Schnorr's, non-Fiat Shamir protocol, these two transcripts let you solve for the witness. Okay, so the gross stuff in the book is explaining that there is a decent probability that the prover outputs this second transcript of this form. So yeah. So to summarize, it's a similar argument to how you show that special soundness of interactive protocols imply knowledge soundness. It has to be different because the Fiat Shamir protocol is not interactive. Okay, and so again, the goal is always to get these two accepting transcripts that share the same first message but have a different verifier challenge, because that's how you solve for the witness. In the interactive case, you kind of just run the prover once, rewind it, start it again with a fresh random challenge. And, it's not that hard to show that you'll get your two accepting transcripts with same first message and different verifier challenge with, pretty straightforwardly. This is another way to get you're running the prover a second time, but you can't just with the random oracle situation, you can't just tell the prover, hey, the random challenge changed, because with Fiat Shamir, the random challenge is replaced by a hash of the first message. So intuitively, you try to, you get as close to that as you can by re-randomizing the random oracle, and you kind of have to get a little bit lucky to, if you change the random oracle, there's like a chance that it changes the first message that the prover selects. These are the gross details I don't want to get into, but yeah, like there is a way to do it so that the prover is pretty likely to the fiat Shamir prover is pretty likely to stick with the same first message as before. But now the random challenge is different. So yeah, so fiat Shamir Schnorr's is knowledge sound, but like fiat Shamir Schnorr's is not special sound. I don't think that even makes sense. Of course, the analysis to show that fiat Shamir Schnorr's is knowledge sound invokes the fact that Schnorr's interactively before you fiat Shamir is special sound. Anyway, so but the one sentence answer to the question you asked like 10 minutes ago was special soundness implies knowledge soundness, but stuff can be knowledge sound without special soundness even making sense for the protocol because it's like non-interactive because fiat Shamir was used or something like that. Is that helpful? Does anyone want to ask any follow-up questions to that?
So I'm assuming there is equivalent to saying knowledge soundness and proof of knowledge as in the literature of interactive proofs.
Yeah. So there's a bunch of weird idiosyncrasies about how you define knowledge soundness, and there might be like slightly different definitions of it, and people will consider related notions like witness extended emulation. To be totally honest with you, somewhat embarrassingly, I always sort of forget the difference between witness extended emulation and knowledge soundness, and why exactly why people go in, consider one and not the other. I'm always able to remember the answers to those questions given enough time. But, I think the high level knowledge soundness just means that any convincing prover must know the witness in the sense that you can actually pull the witness out of the convincing prover's head. And if you leave your understanding of knowledge soundness at that high level and don't go into like weird idiosyncrasies that do come up and are important, for theoretical cryptography, then you could just say, hey, special soundness implies knowledge soundness, but the reverse is not true, and leave it at that.
I wanted to ask a quick question. It might be digressing from the point. Is like the knowledge soundness, when proof of knowledge is defined, it's said that is given oracle accesses to the prover, the malicious prover. But while you were talking about knowledge soundness, I don't think the notion of giving oracle accesses to the malicious prover has been talked about. Is that the point to take home?
Okay, so we gave two different. I sketched two different proofs of knowledge soundness. One for Schnorr's itself, which is interactive, and one for fiat Shamir Schnorr's, which is non-interactive. And so you can just look at what the knowledge extractor had to do in these two knowledge extraction procedures, and that will really be the answer to your question, I guess. The first extractor had to be able to run the prover once, rewind it, and after to the point where it had already sent the first message but not received the verifier challenge, and restart it with a fresh verifier challenge. That's what the extractor, the knowledge extractor for Schnorr's interactive Sigma protocol had to do. That's the kind of access to the prover the extractor needed. And in the fiat Shamir case, the knowledge extractor had to be able to run the prover more than once, where it changes the random oracle between the two runs. Okay. And so that's a different form of access to the prover. Right. Again, the knowledge extractor, for fiat Shamir Schnorr, it's running the prover multiple times, but rather than rewinding it and restarting it, with a fresh verifier challenge, instead it's running it from start to finish again, but with a slightly different random oracle. so that's the kind of access these knowledge extractors need to the prover. And in fact, I'm glossing over further details whereby, like the probability that this knowledge extractor that re-randomized the random oracle actually gets, in the second run of the prover, the transcript of the form that it wants, is actually pretty low. So it might have to run the prover like many, many, many times. Fortunately, like a polynomial number of times, to make it decently likely that it actually gets two transcripts of this form. Yeah, so I think that's the shortest answer I can give to your question is like these knowledge extractors, they certainly need to do more than just like run the prover once and that's it, right? Because if that was enough to extract the witness from the prover, zero knowledge would be contradicted. That would mean that like a single accepting, transcript or whatever, is enough to identify the witness, which of course violates zero knowledge. So these knowledge extractors do need more access to the prover than just run the prover once and that's it. Exactly how much access to the prover do they need sort of varies. Like you have to look at like what the extractor is doing, and it needs to be able to do that. Was that enough of an answer?
So I'm just trying to understand that I got what you're saying. So you're saying that when you say running the prover polynomial number of times, it is okay for me to infer that you actually mean oracle accesses to the prover.
Yeah, this knowledge extractor for fiat Shamir Schnorrs, like what it's doing is it's running the prover like many times, and every time it has to be able to change the random oracle's response to certain random oracle queries that the prover is making. And yeah, so it's you could call that oracle access to the prover, but it's sort of a little more than that. It's like oracle access to the prover, meaning seeing the prover outputs when the random oracle can be, like re-randomized, meaning like you can on the second run of the prover, you're able to change the random oracle's response to some of the random oracle queries that the prover makes. So like if the prover asks the same random oracle query in the second run as in the first run, you have to be able to give the prover different answers in the two runs potentially. The knowledge extractor does. And this gets into all sorts of issues about like, is the random oracle model realistic or not, right? Because like in practice, that random oracle is just like Ketchak or Shah, and so you can't actually, if you query, Shah 256, add a query A, it spits out like deterministically some answer, and you can't go and change the answer. So like, if I actually give you a convincing prover for fiat Shamir Schnorrs in the real world that actually replaces or instantiates the random oracle with Shah, this knowledge extraction procedure doesn't work anymore. This is a knowledge extractor that works in the random oracle model when you can like run the prover a second or third or fourth time and like change some of the answers to the random oracle queries, so that they're different on the fourth run than the third run. That whether that has any implications for the real world is like as much a philosophical question as a technical one. Is that a little bit helpful?
Yes, sir, that's helpful. Thank you.
Yeah. Okay. Yeah.
I wanted to just name one point, which is like when we talk about kind of these different algorithms, she was asking about oracle access, and when the extractor is calling the prover, it's not calling the prover as an oracle, it's calling the prover as an algorithm that like the extractor is allowed to run, and whatever the running time of that other algorithm we're calling is gets factored into our running time. But it's not an oracle, it's like an algorithm we're running, right?
Yeah, I think different things can make sense, and this is getting into the weeds of how you formalize knowledge soundness, and you're probably getting at the issues again. I'm embarrassing myself as like a terrible theorist, but you might be getting into some of the subtleties that lead to people to consider like witness extended emulation sometimes at instead of knowledge. Look at a paper and it defines witness extended emulation and has no definition of knowledge soundness, right? I, I think some of the subtleties are, are you just running the prover, like as a black box and looking at its output, and if so, are you able to then run it a second time and somehow change, like the random oracle it's using, or, ask it different random challenges along the way than you did on the first run. And does it make sense to sort of add the prover's time to the knowledge extractor's time? Or sorry, yeah. All of these questions, I think that there are different answers you could give to them quite reasonably. And there are a lot of theoretical cryptographers that have thought about the kind of the pros and cons and like what the subtleties of different answers a lot more deeply than I have. I mean, there are like really nasty subtleties here. Like, does the extractor run in expected polynomial time or worst case polynomial time, or polynomial time with overwhelming probability, but there's like a small chance it runs forever, all sorts of things like that. And they make a big difference. But I don't necessarily think about those issues myself deeply, so I don't want to dive into them myself. Yeah, but I mean, I think you're right. I think your question is getting at like intuitively what you would like to say is like, hey, if there's a proving procedure that convinces the verifier to accept with decent probability, and the proving procedure is efficient, then there's actually an efficient algorithm for computing a witness from scratch. That algorithm sort of runs an extraction procedure on the prover, and then if the prover itself is efficient and the extraction procedure is efficient, then like you put them together and you just get an efficient algorithm, period. And so if witnesses are hard to compute from scratch, then there just can't be any efficient prover that succeeds in convincing the verifier with decent probability. Like, that is my intuition for like what a security definition should be saying or capturing. But there are very subtle and important reasons why that exact path towards defining things might not quite like work out in the end. Again, some of these extraction procedures might have to call the prover many, many, many times before they actually kind of get out of the prover the information they need to do the extraction. So how you deal with issues like that might change your definitions a little bit. And I kind of would leave it at that for the purposes of this reading group. If I was a slightly better theoretical cryptographer, I might try to say more than that. But yeah.
Sounds good.
Okay. So since we're 90 minutes in, this is actually probably about where we should stop today. Maybe I'll give like, let me just see. Okay. Yeah. So let me just summarize briefly what we saw today. So we saw Schnorr's Sigma protocol for knowledge of a discrete logarithm. So W such that G to the W equals H. Okay. So we saw that it's complete, special sound, honest verifier, perfect zero knowledge. We also discussed that special soundness of this Sigma protocol, which again is it's a 3-message protocol, implies knowledge soundness. Again, the knowledge soundness extractor will sort of run the convincing prover once to completion to get one accepting transcript, rewind it until right after it sent the first message, and run it again with a fresh random challenge. Hopefully that gives it a second accepting transcript. By special soundness, those two accepting transcripts, you can quickly figure out what the witness is from them. We also discussed fiat Schmird, Schnorr's. This is non-interactive, and we said this is also knowledge sound. And again, here the knowledge extractor also entailed running the prover multiple times. This time, like re-randomizing, the random oracle on different runs of the prover. And hopefully, the intuition, to handwave a little bit, is that if you do this enough times, eventually you will get your two accepting transcripts that share the same first message, but have a different verifier challenge. And again, by special soundness of Schnorr's protocol, given those, once you get those two transcripts, you can figure out the witness like immediately. Yeah, and hopefully I gave good intuition, right? Like special soundness is basically just saying that it's checking in the exponent that R plus W times E equals Z, where R and W are not actually known to the verifier or the special soundness, algorithm. But if I give you two accepting transcripts, you get two equations: R plus W times E equals Z and R plus W times E prime equals Z prime. Again, the actual Schnorr verifier is checking this equation in the exponent, and so this is enough to like solve for. So this is how we established special soundness. This is enough to solve for W. I never did the simulator. Oh, I'm sorry about that. Let's do that real fast, and then we'll call it a day. So the simulator to establish that Schnorr is his HVPZK works as follows. So it picks E and Z at random, and then backfills A. So that for any E and Z, there's a unique A that passes the verifier's checks. And so what is that A? So this is the A. This is the check that you have to pass. Yeah. And so if you just set A to be G to the Z times, H to the E inverse, what the simulator outputs is it picks E, it picks Z, and then it sets A to be G to the Z times H to the E inverse. And this is an accepting transcript. Okay, and you can check that this is distributed the same as the honest prover interacting with the honest verifier. Basically, the honest prover interacting with the honest verifier picks A equals G to the R first, then the verifier picks E, and then it sets Z to be the unique value, making the verifier accept, which would be A times H to the E. Okay. So this is the like real transcripts, meaning the honest prover interacting with the honest verifier, and these are simulated transcripts. Okay, and they're the same thing. Like here we have a random A and a random E, and that implies a unique Z. Here we have a random E and a random Z, and that implies a unique A. And it's the same thing. It's the same distribution. Again, the difference between the honest prover that actually knows the witness is, I'm sorry. Sorry, was this? Did I mess this up? No, okay, sorry. I messed this up. Z is the exponent. Z is, yeah. So the way I wrote this, the simulator couldn't do. Sorry, Z gets set to R plus W times E. Sorry. So you have to know W to compute this. Sorry about that. Good. So A is a group element, not an exponent. Z is an exponent. Sorry. So apologies, I botched that. So yeah, but everything else I was saying was correct. So the simulator is choosing the challenge first and the final message, and then computing the unique group element that causes the verifier's check to pass as the first message. The honest prover is choosing the group element first, then it learns the verifier challenge, and then it computes the final message Z. But the honest prover can only compute Z by knowing W. The simulator can compute A, the group element, without knowing W, and it's able to do that because it's backfilling A, knowing what E and Z will be, whereas the honest prover, has to compute A without knowing what E and Z will be. Okay. Anyway, so in one sentence, the way the simulator works is it chooses the final messages at random first, and then backfills the first message. Whereas the honest prover has to, pick the first message first, and only then it learns the second message and has to fill in the third. So that is the simulator that formalizes that the Schnorr Sigma protocol reveals no information whatsoever about W to the verifier. But the intuition, as I explained before, is that this R is randomizing or masking W in this last message Z, so that no matter what W is, by adding this random thing R to it, this last message is just random. And because the verifier only learns R hidden in the exponent, it's unable to kind of solve for W, given that it learns R plus W times E. So this simulator formalizes that the verifier is learning nothing from this transcript, but the intuition is that R is randomizing the last message, and the verifier does learn R in the exponent, but because discrete logs are hard to compute, that's not actually telling it any useful information about R, and hence it gets no useful information about W. Okay, yeah, so that's everything we discussed today. I hope the summary, since it was a pretty rambling discussion, kind of is helpful. We did cover 3 very specific and related topics. Okay, so that's it. Next time we will see Peterson commitments and quickly move from there to polynomial commitment schemes. And I'll just take any questions, and otherwise we will meet next week. Questions?
One question. Go ahead.
So I had a question about zero knowledge here. So yes, last week I think you mentioned that there are like different variants of zero knowledge, and so in particular, like for the different variants of soundness, gives you different variants of zero knowledge. Like there's a statistical zero knowledge and maybe a computational one, I guess. Right. So for this setting, right, for Schnorr or more generally Sigma protocols, is the notion of zero knowledge the computational, or was it because of special soundness or some other variant of zero knowledge, which is like special to this kind of soundness, if you know what I mean?
Yeah. So for Sigma protocols, there's just one relevant notion of zero knowledge, HVPZK. Okay. Which is saying that the simulator is perfect. It's outputting transcripts that are distributed identically to like kind of the honest prover interacting with the honest verifier. Now HVPZK, like in the real world, is not sufficient because there might be dishonest verifiers out there that like deviate from the prescribed protocol to try to get the prover to leak information about the witness. Okay. So if we're just talking about Schnorr's Sigma protocol, like HVPZK is what it's about, but like that HVPZK is sort of not what you want as a standalone thing in the real world. Okay, so for that, I can say two things. Like what in the real world, we typically run fiat Shamir Schnorrs, and I'll discuss that in a second. What notion of zk like that that satisfies. But before I do, I'll say like Schnorr's. There's a short discussion about this in the book. Schnorr's actually is a dishonest verifier. I think it's PZK. With some caveats. Which I don't have cache, but it's like if the challenge that like the simulate somehow the simulator here is only efficient if the verifier challenges come from a polynomial size set, which is not how Schnorr's is really run typically in practice. Like typically the verifier challenge E is a random exponent for a cryptographic group. So typically for elliptic curve groups, E is like roughly it's a random like 256-bit number, right? So the challenge space is massive. It's not polynomial size. And so somehow, if you want to give the simulator, for a particular dishonest verifier, the challenge is coming from some massive space is a problem. And yeah, so Schnorr's does have some security against dishonest security, meaning zero knowledge, proper privacy protection for the prover against dishonest verifiers, but there's just these nuisances. But then, as a practical matter, like I think we, especially in Snark design, like we would only run Schnorr's fiat Shamir'd. And then I think I also put a footnote in the book about this, and it's another one of these just like nuisance things that I shouldn't say too much about. But it's like whenever you fiat Shamir something, if you want to prove anything rigorous about it, you start talking about random oracles. Okay, and zero knowledge is like really subtle and hairy in with random oracles, because there's a big question about reprogramming the random oracle. Okay, and actually this sort of came up when we talked about knowledge soundness of fiat Shamir Schnorr's, right? Because I said, hey, like the knowledge extractor has to run the prover many times, where in like the fourth run, it's going to kind of change the random oracle's answers to some of the queries, right? And so that's like a weak notion of reprogramming the random oracle. Means like you can change, you can run the prover many times, kind of changing the oracle's outputs on different queries. So this is like kind of analogous to taking SHA-256 and changing it. SHA-256 is really supposed to be like a random hash, like chosen at random from some big family of hash functions. And that reprogramming the random oracle like would be like taking SHA and like replacing it with another hash function from the same family or something. And so I think fiat Shamir Schnorr's is probably is PZK in some variant of the random oracle model, so, where you can like reprogram so that's like saying like I can the simulator can like take the random oracle, take the hash function, like fix its answers to some queries, but then set the like completely re-randomize its answers to all other queries or something. Okay, so you just get into this when you try to give the simulator for fiat Shamir Schnorr's, if you just do it as an exercise, you'll quickly run into this issue that like the simulator has to like it has to do this weird stuff to the random oracle. And so, yeah, so those issues, just whenever you talk about ZK in the random oracle model, this programmability issue comes up. Yeah, so in summary, I think up to some small caveats, like Schnorr's is like perfect zero knowledge in whatever setting you want to look at. Fiat Shamir, non-fiat Shamir, but honest verifiers, and and if you fiat Shamir it will only be like an argument instead of a proof. If you don't fiat Shamir it, then it's a proof. Special soundness means it's there's no computational assumption in the special soundness analysis. The prover's claim, of course, is only interesting if discrete logs are hard to compute. But the prover's claim is unconditionally true that it knows the W. It's just if discrete logs are easy to compute, then everyone knows W, not just the prover. So yeah, as far as the variations of the models go, I think ZK you could just call perfect for Schnorr's, and soundness is also sort of it's statistical if it's interactive, and computational if it's fiat Shamir. Did that ultimately wind up in a clear enough place?
Yeah, that's helpful. Thanks. I suppose my question was specifically about the last thing you said, which was the soundness part. So that answers my question. Yeah, so it's statistical for the proof and computational for the fiat Shamir thing. And so it seems like the fact that there's the special soundness doesn't sort of complicate things in terms of the characterization of
No, yeah, I would say special soundness. Schnorr's is sort of funny because this witness that the prover is claiming to know is guaranteed to exist, right? If the group is cyclic, which all of these cryptographic groups we want to use are, you give me any two, group elements G and H, and there's always some W such that G to the W equals H, right? So, what standard soundness doesn't even make sense for this claim, right? Like the prover is not, if the standard soundness basically means, the prover claims there exists a witness satisfying, some property, for circuit sat, it'd be like, the witness satisfies the circuit, calls it to output one, right? That's what standard soundness normally refers to, is like, the prover's claiming there exists a witness, and if the prover is able to convince the verifier with non-negligible probability, then indeed there must exist a witness. Okay, Schnorr's Sigma protocol, the claim is not an existence claim. The existence is given. The claim is purely a knowledge claim. I know the witness. Okay, and once you're in that setting, like special soundness is kind of the best, strongest notion of soundness I think you can hope for, right? Special soundness is intuitively saying, as I mentioned before, like if the prover is prepared to answer even two different random challenges from the verifier, it must know the witness, right? Like that's like being prepared to answer two different challenges is sort of like the very, very weakest condition you could, require out of any interesting prover. And that's already enough to imply that it knows the witness, in the special soundness setting. So I would call this like the strongest notion of soundness like you could possibly define. Once you're in this setting, for like knowledge claims, where existence is like given, and it's the whole issue is like, does the prover know the witness or not? And so the fact that Schnorr's is special sound means like any notion of soundness you might be interested in, Schnorr satisfies it until you fiat Shamir it, and then that brings in only computational soundness. Is that a helpful sort of rambling response?
Yes. Yes, that's very helpful. Thank you.
Great. Yeah. So special soundness is special, right? It's like there are weaker notions of soundness you could consider, but Schnorr satisfies even the special one that's kind of the strongest you could possibly hope for, and Schnorr's has it until you Fiat-Schmier it. Cool. Other questions? All right. So next time we'll talk about Peterson commitments. It's pretty cool. Like you can commit to values without revealing any information about the committed value. And then, as we'll discuss, you can start to prove things about the committed values without revealing anything about the committed values besides that they satisfy the properties you're proving. So we'll see that next time. And then the time after that is polynomial commitments finally. So thanks for bearing with all the rambling this week. Feel like it was more rambling than usual. And next week, maybe I'll do a little better. Yeah, so see you in a week.